Hey everyone, welcome in. We're diving into something pretty incredible today, something really cutting edge.
Yeah.
IBM's Majorana 1 quantum chip.
Really exciting stuff.
And, I think for anyone listening who's like me, you want to keep up with these massive tech jumps, right?
Sure.
But without needing a PhD in physics.
Totally. It can get pretty complicated fast.
Exactly.
Yeah.
So we're going to break it down, make it clear why this is a big deal and what it could mean for the future. Basically, how quantum computing is getting a huge boost.
A huge boost, yeah. And what sets Majorana 1 apart is it's not just an upgrade, it's like a whole new approach to building quantum computers from the ground up.
Like changing the foundation.
Absolutely. And coming from IBM, a real powerhouse in this field, it shows how serious they are about making quantum computing actually useful in the real world, not just theory anymore.
Okay, so let's start with the name, Majorana 1.
Oh,
Sounds like something straight out of sci-fi.
it does, doesn't it?
But it's actually named after some pretty fundamental science, right?
Oh, yeah, absolutely. It goes all the way back to the 1930s to an Italian physicist named Ettore Majorana. He predicted these particles, hypothetical particles called Majorana fermions.
Okay.
And what's wild about them is they're their own antiparticles. It's kind of mind-bending.
Wait, break that down for me, because...
So think of it like this. Every particle we know has an antiparticle. It's opposite, same mass, opposite charge.
Got it, like matter and antimatter, that whole thing.
Exactly. But Majorana fermions, if they exist, they wouldn't need a separate antiparticle. They're their own opposite.
Wow, that's a head-scratcher for sure. But how does that tie into building a better quantum computer? What's the real-world advantage here?
So the big advantage is it could let us make way more stable qubits. Now, qubits, they're like the basic units of information in a quantum computer, kind of like bits in your regular computer.
Yeah, that part.
But here's the thing. Regular bits, it's a 0 or 1. Qubits, they can be both at the same time. It's called superposition.
Right, right. The quantum weirdness.
Yeah, and that lets them do these crazy complex calculations way faster than regular computers. But the catch is, these quantum states, super fragile, easily messed up by noise, temperature, anything really.
Oh, I see. So they're powerful but finicky.
Exactly. Leads to errors, limits what quantum computers can do, how long they can run calculations. The idea is, if we can base qubits on Majorana fermions, they'd be way more stable because of how these particles work. Less errors, more reliable.
So that's the big hurdle in quantum computing, right? This instability, these errors in the qubits.
Yeah.
And Majorana 1 is IBM taking that head on.
Yeah, spot on. It's part of their big strategy to get quantum computing ready for prime time, to actually solve real problems. And you can't do that with unreliable qubits. You need to scale them up, make them work reliably.
Right, because scaling up with tons of error-prone qubits, that just wouldn't work, would it?
It'd be a mess. So Majorana 1 is tackling that, trying to get us closer to truly reliable quantum computers.
Okay, so how's it different? We keep hearing about topological qubits. What does that even mean?
Okay, so imagine this. Regular qubits, they usually store information in the energy states of single particles or in tiny circuits, superconducting circuits, but that makes them vulnerable because the information's all in one spot.
Yep.
Topological qubits, they're different. They encode information in the overall shape, the structure of the system. Like imagine weaving a pattern into a fabric.
Okay.
You snip one thread, the whole pattern doesn't come apart. It's in the arrangement itself.
Oh, that makes sense. So it's not localized, it's spread out.
Right, so it's more resistant to disturbances like noise or temperature changes, because a little disruption won't destroy the whole thing.
So the information is more robust, I get it. And IBM's using superconducting qubits for Majorana 1, right? How does the topology thing fit in with that?
Good question. Superconducting qubits, they're pretty common. They use these circuits that work at super low temperatures.
Where materials become superconducting.
Exactly. Electrons flow with no resistance, helps maintain those delicate quantum states, and they've been key to a lot of progress in quantum computing.
But they're still prone to errors, right? Like we talked about.
Right, that's the issue. So Majorana 1 is an experiment in how to add topological properties into these superconducting systems.
To make them more stable.
Yep. Using those predicted stable properties of Majorana fermions to try to make those qubits less error-prone within the superconducting framework. Goal is to really cut down those error rates that are holding superconducting quantum computers back.
Okay, so it's not just an improvement, it could be a whole new level of reliability.
Yeah.
What's the end game here? What becomes possible if we can actually get this stability working?
Well, the ultimate goal is what we call fault-tolerant quantum computing.
Fault tolerant, meaning?
It means you can do all those complex calculations without constantly worrying about errors messing everything up.
Hmm.
Imagine trying to use a regular computer where every calculation had a high chance of being wrong.
It'd be useless.
Right. Same with quantum computers. To run the really big, complicated algorithms we need to solve those super hard problems, you need qubits that can hold their state for a long time without too many errors. Fault tolerance means we can correct those errors efficiently so the overall computation stays reliable, even if it's incredibly complex.
So basically, it lets us actually use the power of quantum computers for real.
Hmm.
And you've mentioned some pretty mind-blowing applications, things like cryptography, material science.
Yeah.
What are some specific examples of how a reliable quantum computer would change things?
Oh, so many. In cryptography, for instance, a fault-tolerant quantum computer could potentially crack a lot of the encryption methods we use today to keep our online communications secure.
Like breaking the codes?
Basically, yeah. Think about RSA encryption. It protects tons of stuff online. A powerful quantum computer could break that, so huge implications for cybersecurity, both good and bad.
Right, huge implication.
Then there's materials science. Quantum computers could simulate molecules and materials with insane accuracy, letting us design totally new materials with specific properties.
Like designing materials from scratch.
Exactly. Maybe for better batteries, lighter and stronger building materials, even new types of superconductors. It could revolutionize industries. And drug discovery, imagine speeding up the process of developing new medicines by accurately simulating how molecules interact.
That could be life-changing.
It really could. Quantum computers would let us process huge amounts of data in totally new ways. We're just scratching the surface of what's possible.
Sounds like it could change almost everything. So, where does Majorana 1 fit into IBM's overall plan for quantum computing?
It's a key step in their quantum roadmap, their plan for scaling up these systems. They're not just focusing on making more qubits, but also making them better, more stable.
Quality over quantity, in a way.
Exactly. And Majorana 1 is a big part of that. It's a specific approach to get those reliable, error-resilient qubits that they need for large-scale, useful quantum computers.
So it's not the end goal, but a crucial step towards it.
Right. It's a milestone, a sign of real progress towards those practical quantum computers we've been talking about.
Of course, it's not all smooth sailing. You mentioned it's early days. What are some of the big challenges ahead?
Oh, plenty. Even though the potential is huge, we're still at the beginning. Majorana 1, it's the first version. There'll be many more, lots of improvements to come. And from a purely technical standpoint, just creating and controlling Majorana fermions is super hard.
Like experimentally.
Yeah. And then there's scaling it up. Building one stable topological qubit is one thing, but imagine building a whole computer with hundreds, thousands, maybe even millions of these things, all connected and working together.
Sounds like a nightmare.
It's a huge challenge. And then there's keeping these systems stable for long enough to do meaningful calculations. Quantum systems are unbelievably sensitive. Keeping them in those delicate states for any length of time is a constant battle.
So it's not just about the initial breakthrough. It's about refining it, making it practical, getting it to a point where it can be used widely.
Absolutely. We need more advances in materials science, nanofabrication, our basic understanding of how these quantum phenomena work. But the work IBM's done with Majorana 1, it's really encouraging. It shows that these complex theories can actually be turned into real hardware.
A proof of concept.
Yeah, exactly. And that gives us a foundation to build on to keep researching, experimenting, and developing. Every step forward, even if it comes with new challenges, gets us closer to really unlocking the power of quantum computing.
So to sum it up for our listeners, what's the main takeaway about IBM's Majorana 1?
I'd say the key thing to remember is it's a big step forward in making stable, scalable quantum computing a reality. By exploring these topological qubits and the potential of Majorana fermions, IBM is pushing the boundaries of what's possible in quantum systems.
And while it's still early, the impact down the line could be huge.
Oh, absolutely. We're still figuring things out, but the potential applications across so many fields are just enormous. It could completely change how we think about computing power.
It really makes you wonder, what breakthroughs are just around the corner? Things we can't even imagine right now. It's an exciting time to be following this field. Thanks for joining us for this deep dive today.
My pleasure. It was great to be here.
Always fun to talk about the future of computing.
Yeah, who knows what's next? But it's going to be wild.
Absolutely wild, that's for sure. All right, everyone, until next time.